This is Professor Mark Barkey at the University of Alabama, and this is the course AEM 649 Fatigue Analysis. Now, I've already given kind of an overview of the course in a separate video, so in this video we'll start to get into some of the details of what we're going to do in this class and how we're going to approach fatigue analysis. So as a motivating item that I often do in fatigue class, and I'm not alone in this, a lot of people do this sort of thing, is if you have a class full of people, you hand out paper clips to everybody. And you can do different things, and one of the things that I like to do is kind of divide the class up into half and say, okay, I want the side of the class on the right side to take that paper clip, and I want you to count how many times it takes to bend that paper clip into a 90-degree angle until it finally breaks. And on the left side of the class, maybe use a 45-degree angle and see how many times it takes before you break that paper clip. So everybody's familiar with paper clips. These paper clips that I'm showing here, these are actually steel. I can't really tell you what type of steel it is, but it's a metal. And if we fatigue it enough, it will break. So anybody in this class probably has an idea somewhat of what fatigue is all about, and we'll get into those details more formally in a little bit. But you can do this at home too, so take a couple paper clips and bend them back and forth. So I did a couple here to 90 degrees, and I got 10 cycles and 13 cycles. I did one of them at 45 degrees, and I got 24 cycles. The 90-degree bend has effectively a higher load or larger deformation than the 45-degree angle. The higher the loads, the less cycles it'll take before the thing breaks. And this is something that we'll see quite usually in fatigue of materials and fatigue analysis. Higher loads have shorter lifetimes, called low cycle fatigue. Smaller loads have higher lifetimes, called high cycle fatigue. Now, I would classify both of these as fairly low cycle. High cycle fatigue may be on the order of 1,000,000 cycles. All right, well, we've noticed that observation that this graph, if we were to plot it with the load on the vertical axis over here and the life on the horizontal axis, takes a plot like this, so it slopes downward to the right. But also with that data for the 90 degrees, we're not necessarily going to get the same exact number each time we repeat our experiment. Now, I have the data from the last class. Let's see if I can pull it up. And so we can see some of the variation in the data here. So at 90 degrees, somebody got 5. Somebody said they got 5.5. We'll talk about what a half cycle might mean a little bit later. 8, 3, 6, 10. Someone got 21. Somebody even got 34 cycles bending it to 90 degrees. They must have got a pretty good paper clip, because some of the people at 45 degrees got as few as 9. Some of them got more than 34. They got 45 cycles. You can see the numbers there. And then you see the ones down at the bottom, down here, 37, 46, 35, and 35. Those students got tired of bending their paper clip. So we put the little arrow next to that value indicating that we got the value of 37, but if we kept testing, we may have gotten a higher value. Maybe it could have been 38, maybe it could have been 100, but we got a different value for that. All right, and so I kind of like to do a outline format of my lectures, so we can call this topic 1, item A, looking at the paper clips. All right. So again, it's kind of a nice motivational thing to do to see what's going on. Now, the next section, I'm going to kind of copy and paste some text to keep me from having to write so much. I can type it a little bit faster. So let me get this pulled up and then I'll kind of read through and explain some things in a little bit more detail. So we can look at an overview of the fatigue process and what causes it. And we've seen this in the paperclip experiment that we just talked about. Fatigue is a damage process by which irreversible changes are made to a material by the repeated application of load. Now there's a couple of key items here in that statement. We get damage in the material. I mean, something isn't the same as what it used to be. Something has changed. And usually when we talk about damage, we mean to its detriment. And it's under the repeated application of load. Now there are different ways that you can get damage in a material. You can take a material and shoot it out of a gun and have it impact a target. And that bullet or projectile may get destroyed as it hits that target. Well, that's damage, but that's not fatigue damage. Okay? You can get damage in the target. Some of it may flake off. That would be like spalling. So spalling is a damage, but it's not due to the repeated application of load. That happens kind of suddenly. We also have damage processes that change over time, such as creep in the material, the eventual void formation and relaxation of the material due to creep damage. So we're not talking about that here. And these are all different important aspects of damage, but the one that we're going to talk about in our class is the fatigue process, which does depend on the repeated or alternating application of load. So load and unload, high load, low load, back and forth through different levels of load is what's going to cause fatigue. All right. For engineering applications, fatigue damage may eventually render the structure inoperable by eventual rupture or final fracture, or through structural degradation. So certainly if you're in a car and the wheel falls off because it has been cycled many times, that would certainly be a problem for the car. But even things such as maybe some welds breaking a little bit, having some damage at those things, may cause the structure to behave in different ways than what it had before. Usually in this case, the structure would be less stiff. So that's what I mean by structural degradation. Of all the things that have an effect on the fatigue process and the fatigue life of a component, it would be the composition of that component, that would be the material that we use that has the largest effect. So obviously we wouldn't expect a piece of steel and a piece of plastic to have the same type of fatigue life, but even different grades of steel, even different types of steel, different alloys, that composition that makes that alloy will have an effect on what happens to that material when it's subjected to fatigue. Now, of course, the material composition isn't the only thing that affects the fatigue life. How that structure is designed, whether or not it has stress concentrations in it, for example, the manufacturing process, stamping or machining, that sort of thing, the service environment, and the load levels, of course, all affect the fatigue performance of the structures. So we're going to take a look at a lot of these different aspects, and we'll learn how to incorporate this into the kind of fatigue data that we might get in a laboratory environment. All right, so what goes on in this fatigue process? Let's spend a few minutes to talk about the fatigue damage process and some of our familiar assumptions that we might have in engineering and engineering design. So probably one of the most common engineering analysis simplifications that we can make is that materials and systems act in a linear manner. So in other words, Hooke's law. Of course, Hooke's law, we would write this as F is equal to Kx. And that comes about through a spring being loaded and observing what happens to that spring. If we put a load on this and we have certain spring stiffness, then the load and the deflection of that spring, if it's a linear spring, are linearly related. As we increase the force, we have an increase in deformation. As we remove the force, we have a decrease in deformation until we get back to its equilibrium position. In other words, when we have this linear system, when the application of load is removed, the original state of the system is fully recovered. That's the assumption with linear elastic behavior. I know many of you have done linear elastic finite element analyses. You're assuming that this thing, whatever object structure you're looking at, behaves like a giant spring. When you get down to it though, if you have a real material that you load and you unload multiple times, the original state of the system isn't really always fully recovered. Some energy is going to be dissipated each time, usually by heat, and the entropy will increase. Usually this amount of heat that's generated is pretty small, but it doesn't have to, and this heat can work in different ways. This dissipated energy is from things that change in the material that don't go back to their original positions. In metals in particular, you might have an atom that moves into a vacancy, or a group of atoms may slide like a slip system or a slip plane. You may have dislocations in the metal. In polymers, you have weak bonds that can break. The chains may stretch out and they may reorient themselves, even though macroscopically the thing is pretty much the same looking if you don't exceed the load very much. Some things have changed inside that material. In ceramics, you may have an ionic bond that may suddenly give way. So from the global view, it doesn't really look like you're changing the material, but from the micro view, the microstructure of the material has somehow been altered. All the fatigue failures and the damage that we're talking about come about from initially very small changes in what goes on microscopically in the material. So these things that go on, the slip systems and whatnot, these small changes can accumulate to cause internal redistributions of stress and strain in the material. And then small cracks can form that lead to eventual structural failure. So there are a lot of different points of view we can take to study fatigue. We can look at microstructure, be very focused on that aspect. We can take a look at very small defects like small cracks and so forth. We take the point of view of structural design or manufacturing and so forth. And while all of these points are good points of view to study fatigue from, for our class, which is a class in fatigue analysis, we're going to study the engineering methods for computing the useful life of engineering structures. All of these things are important. The microstructure and the material properties are very important, and we will need some way to quantify the material properties and be able to use them effectively. But in our class, we're not going to be very concerned about the specifics of the slip planes and dislocation development and so forth. We're going to leave that to the metallurgists to look at that aspect, and from their perspective of teaching the class, then they will have that aspect. Someone that is going to make a career in fatigue and durability analysis should have kind of all aspects of fatigue learned and covered. For our class, again, we're going to look at the analysis of structures to calculate fatigue life. So we're not going to be getting into detailed material science, but we do need to remember that the origins of fatigue damage very much depend on the material composition and the material science level. Fatigue damage can occur in any engineering material. Our initial focus in our class will be on metal fatigue. The things that we learn about metal fatigue can be applied to other materials, such as composites and ceramics and polymers and so forth, with suitable modifications. And as we have time in class, we're going to take a look and talk a little bit about other types of material systems and what changes in our framework we can develop to accommodate them. Composites and polymers are the other two that I'm most familiar with. I'm most familiar with metal fatigue, but I've done some work in both of those other areas. I don't have any personal experience in ceramics, and typically those get involved in some fairly specific applications, some very important but very specific applications. And in those cases, sometimes things other than just fatigue damage are important for those materials as well. So there's many places that we can start when we start talking about fatigue analysis, but I think personally a good place to start is taking a look at time histories of load. We said that we had to have a repeated application or alternating load applied to our component in order to have this fatigue process. So let's classify or explain some different things when we take a look at time histories of load. And our initial discussion is going to be kind of motivated by historically how things have been looked at for fatigue analysis. Certainly fatigue has been around for a long time, but the systematic analysis of fatigue was really started by a man named August Wöhler, who studied failure of train axles. All right, so in the 1800s, transportation of materials and goods by rail was becoming very common. And if you're familiar with the way train axles are, I'm going to draw kind of a poor sketch, but it'll work for our purposes. We can think of a train axle, which is really a big circular metal, steel bar. We have a couple of wheels attached to it. Okay, and this of course would be the thing that sits on the track. The reaction from the track is up this way. And then train axles usually are used in sets, and they're attached to each other by the side frame, which transmits the load from the car to the axle. Now the side frames actually sit on the outside of the wheel, and at least in modern trains that I'm familiar with. So that presents a downward load this way. And maybe I can use a different color. If we track what happens to a point on the outside surface of this round bar, okay, so we have a circular cross section. If this were a problem in static loading, we would be familiar with our formula that sigma is equal to my over I. We would plot the shear force and bending moment diagram for this beam, this beam-like structure. The shear force diagram would go down, it would go over and up, it would have zero shear in between, it would go up, over, and down. So this would be what the shear diagram would look like. The moment diagram for this structure would do something like this. It would slope down, it would hold constant in this zero shear region where it's not changing, and then it would slope back up. So these would be the key points here. And in between the wheels, then, we have a constant bending moment. So if we think of this as an elastic loading situation, we've identified the centroid of that. The distance from our centroid to where that point A is at, we call that distance y. Y, not y bar. And that point on top would be in compression, so we would say that the stress at that point would be equal to minus m times y over I being the moment of inertia of the section. If the load is constant and the cross-section stays constant, the stress changes with this position y. Let's take a look at that in a little bit more detail. Okay, so I've drawn a sketch with a little nicer circle there. As the shaft rotates through some angle theta, the height y will change. Of course, when theta is down here at 0 degrees, then y is equal to 0. When theta is up at the top at 90 degrees, then y is equal to the radius of the bar. But in general, we would say that the height y would be equal to r sine theta. Okay, so there's a little bit more room there. Now, if the shaft is rotating at a constant angular velocity, then our stress would be proportional to, of course, m over I times this height, the y distance. We would say that, given all the other things being constant, that the stress would be proportional to sine omega t. And as it goes up to the top, we would get one value of stress, say negative, and as it goes down to the bottom, we would get another value of stress, say positive, depending on how the bending loads were acting. And so if we were to plot this out, starting with theta is equal to 0, we would have a sine function. And this particular type of time history is called a fully reversed constant amplitude load. We'd have one cycle of load that goes from here to here. We would have a maximum stress and a minimum stress that would be defined in these ways. So as we do fatigue testing today, even though we don't often use rotating bending, at least in my lab, I often still use fully reversed constant amplitude sine wave type loading that's digitally controlled by the controller on the testing machine. Now, in addition to that, we could have constant amplitude loading that's not fully reversed. And so in those situations, we would have some cycle that was offset from the zero load. Okay, so this would be stress on this axis and time on this axis. And so we could have a waveform that was up here. Now there are some important terms that we're going to be using a lot in the class. We've already talked about a cycle. It's a complete up and down of this. So from here to here would be one cycle. from this point back to this point again would be a second cycle. We can talk about the amplitude of the cycle. And we can talk about the stress range of the cycle. The stress range would be from the peak to the trough. Okay, and that would depend on the maximum and minimum stress. So again, we could have the maximum of the cycle and the minimum of the cycle. And the stress range, delta sigma, would be the difference between those two. We can also see that the stress amplitude would be half of the range. And then this place where these stresses cycle about is called the mean stress. Now there's another term that some of you may be familiar with, particularly if you've already had some experience with fracture mechanics. That's called the load ratio. It's usually expressed as R, and R is defined as the minimum divided by the maximum stress. All right, so in this case, this point would be the maximum stress, this would be the minimum. We would have a value of the R ratio that is not 0. If the minimum stress went all the way down and touched this axis, then the minimum stress would lead us with an R ratio of 0. You can't really fully describe something with just the R ratio, but it does give you an idea of whether or not you have a tensile type waveform or a tension and compression type waveform. So if we had R is equal to -1, what that would mean is that we would have a fully reversed type situation where the maximum stress and the minimum stress have the same magnitude but the opposite sign. Like we had on the previous page. So the graph that I'm showing here is kind of a generalization of what we saw on the previous page, where we could have a mean stress offset. Now we'll learn that non-zero mean stresses can affect the fatigue life. In fact, positive mean stresses, where you have a tensile mean stress, usually is to the detriment of fatigue life, where a negative mean stress is usually helping the fatigue life. Now there's another type of loading that I'm going to show you and that you're going to work with in our class, and that's going to be called variable amplitude loading. So again, if we have stress on this vertical axis and time along this axis, variable amplitude loading just kind of goes all over the place. Okay, how might you get this type of loading in a component? Well, if you're in an aircraft and the wind is gusty on the wings and the wings kind of move up and down a little bit more when the wind is changing, then you may have some peaks, and you may have a whole bunch of little small things as things are just kind of vibrating along at small amplitudes. So this variable amplitude loading is common in any kind of transportation system like cars and aircraft, and even to some extent even in the railroad industry, although that tends to be much more constant amplitude loading on the axles. You could have some situations where you have more variable loading if you kind of look at the overall system as it stops and starts and so forth. Now, a lot of the things we talked about in the previous slide with the mean and all that doesn't necessarily look like it makes a lot of sense right now, because we have all these things that are kind of small cycles and big cycles. So in a way, what I've drawn here can almost look like the situation where I have kind of repeated large cycles, kind of an overall sine wave happening, but superimposed on that is a whole bunch of smaller, higher frequency, smaller amplitude, higher frequency cycles on top of it. We will eventually learn how to handle this type of loading, and that deals with our project. And in our project, I'm going to have you analyze a couple of time histories related to a ground vehicle. One's a pothole type load, and one is a rough road type load profile. And they're kind of interesting in that they have some, they look a lot different. The pothole is easily identified to be different than the rough road type situation, but both can contribute to fatigue damage. So at this point, what I'd like for you to do is to take a look at the lecture on the project overview. I want you to read about the stress life approach in whichever book you're using. We've talked about those options already. And then I want you to take a look at the details. I want you to watch the project video on peak picking. And in there it talks about how to make a computer program for determining peaks and valleys and rearranging a variable amplitude time history. Now, I want you to get started on that soon in the semester so that you're able, in a position to make good progress on it later. The exact reasons why we're doing the things that we're doing in that program will be revealed later as we continue our lectures. But we kind of need to process some of these things in parallel so that it's not all on you in 1 week to come up with your variable amplitude fatigue calculation program. We'll kind of stretch it out and see if you have any questions about things as we go along. All right, so I think that's good for our first lecture. We'll get into more details about our fatigue analysis and our stress life approach to fatigue in the next lecture.